Imagine for a second that the artificial intelligence writing your emails or, analyzing your company's data.
Right, we're coding your next app.
Yeah, exactly.
Yeah.
Imagine that it isn't just a clever piece of software. Imagine that its fundamental behavior, its safety constraints, all of it, is governed by the exact same mathematical laws used to calculate the entropy of a black hole.
I mean, it sounds like an absurd science fiction premise, or maybe a really late-night dorm room theory.
Love it.
But if you actually look at the math structurally, it is an observable reality. We are basically looking at a scenario where the cutting edge of computer science is just a mirror reflecting high-energy theoretical physics.
Which is wild. So, welcome to the deep dive. Today, we are looking at a 2026 paper from the ACRA Insight LLC research group. It's called Architectural Determinism.
And this paper basically accuses the biggest AI labs in the world of not doing computer science at all.
Right.
It says they're actually doing quantum gravity in disguise.
The core thesis here is just mind-bending for you as a listener to consider. It argues that AI labs aren't just reacting to technical constraints or market pressures to build these models.
No, not at all. Instead, they are building literal silicon isomorphic projections of their founders' doctoral obsessions.
Okay, let's unpack this. The paper zeroes in specifically on Anthropic.
Right, one of the leading frontier AI labs.
And specifically, its two founders, Jared Kaplan and Sam McCandlish. Now, before they were building massive AI models, they were elite theoretical physicists.
Elite is the key word there. And what the researchers at ACRA found is an explicit, mathematically verifiable correlation here.
A correlation between what they were doing in 2009 and what they're doing now, right?
Exactly. The highly theoretical physics problems Kaplan and McCandlish were working on back then, specifically something called the AD-SCFT correspondent.
Which we'll get into.
Yeah, but they connected that directly to how they went on to design Anthropic's flagship safety architecture, which is known as constitutional AI.
I'm looking at this paper, and it essentially claims that when you ask an AI a question, the way it refuses to answer a dangerous prompt is a direct inheritance from a physics lab nearly 2 decades ago.
It's all connected.
I want to figure out how we bridge this gap.
Right.
Why does a paper on AI safety care about black holes?
Well, to bridge that gap, we really have to understand the specific intellectual water Jared Kaplan was swimming in during his 2009 Harvard PhD.
Right.
We have to go back to a massive breakthrough in physics that happened in 1996. It was led by a physicist named Juan Maldacena.
Maldacena, okay.
Yeah, and he was trying to solve a problem involving black holes and string theory.
Okay, looking at the notes here, it points to his 1996 thesis. It says he was looking at the Bekenstein-Hawking entropy of a D1, D5P black hole.
Which is a mouthful.
Yeah, if I'm listening to this while driving to work, that just sounds like a random string of sci-fi words. What makes a D1, D5P black hole different from, say, a normal black hole, the one in the middle of our galaxy?
That is the perfect question to ask. So, a normal astrophysical black hole is incredibly messy.
Because it's from dead stars.
Exactly. It's formed from collapsing stars, it has rotation, it's chaotic. But a D1, D5P black hole is a highly idealized theoretical construct. It's used in string theory.
So it's basically just math.
Basically, yeah. Think of it as a perfectly pristine mathematical black hole built out of fundamental strings and membranes.
What physicists call D-branes, right?
Right. And Maldacena used this pristine model because he specifically wanted to calculate its entropy.
And entropy, just so we are totally clear for everyone, is fundamentally about information.
Yes, exactly. In the context of information theory and black holes, entropy is just a measure of the internal information, the hidden states of a system.
Okay.
Because for decades, physics had this huge problem. The traditional view of a black hole was that its interior, what they call the bulk, is infinitely dense and totally unknowable.
Right. The old saying that if you throw an encyclopedia into a black hole, the information is just gone.
Lost forever. But Maldacena proved something revolutionary.
The paper says he proved the entropy could be calculated entirely from the boundary, which is crazy. It says he used something called the Carty formula to microscopically reproduce the exact entropy just by counting degrees of freedom on the surface. How does a formula do that?
Well, the Carty formula is a mathematical tool used in 2D systems, specifically two-dimensional conformal field theories.
Okay.
It counts how many possible quantum states exist at high energies. So Maldacena essentially looked at the 3D black hole.
The interior part.
Right. Then he looked at the 2D surface wrapping around it. He applied this 2D formula to the surface, and the number he got perfectly matched the known 3D internal entropy.
Wait, really?
Perfectly matched.
So the surface of the black hole, just a two-dimensional boundary, contains all the information needed to describe everything happening inside the 3D space.
That is the massive paradigm shift. He showed that the boundary is not just a wrapper. It is a mathematically sufficient representation of the entire bulk. And this specific calculation led directly to his much more famous 1997 breakthrough, which is literally the cornerstone of this entire AI discussion.
Okay, lay it on me.
The AD-SCFT conjecture.
The anti-de Sitter conformal field theory correspondence? That sounds intimidating.
It does.
I'm looking at this equation in the notes. HCFT equals HADSQG. The paper emphasizes this as an exact equivalence. Can you break down what these two sides actually represent?
Let's strip away all the jargon. On the right side, you have AD-ESQG. That stands for anti-de Sitter space with quantum gravity.
What?
Imagine a snow globe. The inside of the snow globe, the 3D space where gravity exists and the little flakes move around, that is the IDS space. It's the bulk.
Got it. I have the 3D interior of the snow globe in my head.
Now look at the left side of the equation, CFT, or conformal field theory. This represents the glass surface of the snow globe.
The outside.
Right. It is a lower dimensional boundary. And crucially, there is no gravity on this surface. It's just a flat boundary with interacting quantum fields.
And the H in the equation, that stands for Hilbert space.
Yes. The Hilbert space is essentially the total catalog of every possible state a system can be in.
Okay, so a massive catalog.
Exactly. And what Maldaceno's equation boldly claims is that the complete catalog of states for the 3D interior with gravity,
the inside of the globe,
is completely identical to the catalog of states for the 2D surface without gravity.
I want to make sure I'm visualizing this correctly. Is this like a 2D credit card hologram?
Oh, that's a good way to look at it.
You know, the ones where you tilt the flat card and you see a full 3D image floating inside it?
Mm-hmm.
If I scratch or change a pixel on that flat 2D surface, does it mathematically alter the 3D projection inside?
That analogy actually captures the mechanics beautifully. In a hologram, a 3D image is entirely encoded in a 2D interference pattern.
Right.
If you change the 2D pattern, the 3D image you see must change, because the 3D image is entirely projected from that 2D data.
So the ADA-CFT correspondence says our universe acts the same way.
Or at least this specific theoretical model of it, yeah. The interior geometry must adjust to remain consistent with whatever's happening on the boundary.
Okay, and this brings us back to Jared Kaplan, the Anthropic founder.
Exactly.
The paper notes that his 2009 doctoral work and also his 2016 lectures at Johns Hopkins were completely focused on this, like obsessed with it. He was teaching something called the GKPW relation.
Yeah, the GKPW relation. It's named after the physicists Gibser, Klebanov, Polyakov, and Witten.
That is quite the lineup.
It is, and it's basically the actual mathematical dictionary that translates between the 2D surface and the 3D bulk.
So Maldacena gave the concept, but they gave the translation.
Right, Maldacena gave us the concept that they are equal. GKPW gave us the exact mathematical translation manual.
Okay, I'm following.
It equates the gravitational behavior in the interior with the boundary behavior. It tells you exactly how a change on the surface physically forces a change deep inside.
The source text gets into a mechanism here called the UVIR correspondence. It talks about mapping the radial coordinate Z to the renormalization group energy scale.
Yeah, that gets pretty deep into the weeds.
Let me try to act as the translator here, and you tell me if I'm totally off base.
Go for it.
So the boundary is the UV, the ultraviolet, representing high-level, zoomed-out data. The deep bulk, the center of the snow globe, is the IR, the infrared, representing the fine-grained microscopic dynamics.
Well, you're touching on the right concept, but let's just clarify the mechanism a bit.
Okay, fix it for me.
In physics, when we talk about the UV, the ultraviolet, we mean very high energy, which actually corresponds to very short distances or fine grain detail.
Oh, so the opposite of what I said.
Kind of, yeah.
Right.
When we move away from the boundary into the deep bulk, the IR, infrared, we are moving to lower energies.
Which
corresponds to looking at the system from further away, the macro, high-level picture.
Ah, I see. So moving physically deeper into the bulk space is mathematically identical to zooming out and looking at the system's broader macroscopic behavior.
Yes, exactly. The math dictates that whatever rules you set on the boundary strictly control the macroscopic, zoomed-out dynamics in the deep interior.
Wow.
Physics spent decades grappling with this problem of minimum sufficient representation.
Like, how much data do you actually need?
Right. How do you compress a massive high-dimensional reality into a lower dimensional space without losing information? The holographic principle solved it.
And the paper points out a specific contribution Kaplan made in 2011, something called the Mellon representation.
Yeah.
It says he framed complex holographic correlations using Mellon amplitudes with poles corresponding to intermediate states.
Right.
Now, the paper claims this mathematical structure, like predicting intermediate states based on contextual constraints, is structurally identical to how a large language model predicts the next token.
This is exactly where the bridge from physics to AI starts to form.
Okay, walk me through that.
In physics, Kaplan was using Mellon amplitudes to predict what happens when particles scatter and interact in this holographic space.
He was predicting intermediate states.
Right, based on the constraints of the boundary. Now, think about an AI. In a large language model, the system is predicting the intermediate state, which is just the next word, based on the constraints of the context window.
So the context you type into a prompt, like if I ask it a question, that acts mathematically like the boundary constraints in his physics equations.
That is the epistemological habit the paper is talking about. Because Kaplan spent a decade viewing incredibly complex systems through this specific holographic lens, he just didn't approach AI the way a traditional computer scientist would.
Which perfectly sets up the pivot to 2020.
Oh, absolutely.
Because I remember the AI landscape back then. Researchers were constantly fiddling with the architecture.
They were trying everything.
Right, they'd add a new layer here, tweak an algorithm there, trying to squeeze out a tiny bit more performance, treating neural networks like complicated software engineering problem.
Yeah, very microscopic tinkering.
But Kaplan comes in and basically says, stop fiddling with the microscopic code. Let's look to the macro laws.
He brought a physicist's methodology to machine learning.
Which makes sense.
A traditional computer scientist tries to engineer a clever new trick. A physicist assumes the system is already governed by natural laws and just tries to discover those laws.
And this mindset triggered the publication of the famous 2020 Scaling Laws paper by Kaplan and his colleagues at OpenAI.
It was a total watershed moment.
This is the paper that basically told the entire tech industry, hey, just make the models bigger, give them more data, and we can predict with mathematical certainty exactly how much smarter they will get.
It sparked the massive arms race we are in right now. What Kaplan and his team demonstrated was that AI cross-entropy loss follows precise, predictable power laws across 7 orders of magnitude.
Okay, let's break down cross-entropy loss and power laws for us. What were they actually measuring?
Cross-entropy loss is essentially a metric of how confused the AI is, or how often it makes a mistake when predicting the next word.
So lower loss is better.
Exactly. The lower the loss, the smarter the model. Now, before Kaplan, many AI researchers just assumed that as you made a model bigger, its learning curve would look like an exponential curve.
Meaning it would get better really fast and then just suddenly plateau.
Right, just stop improving no matter what you did.
The text actually has a great quote about this. Kaplan admitted to questioning AI researchers who assumed learning converged exponentially.
I love this part.
He said he would ask dumb questions like, are you sure it's an exponential? Could it just be a power law?
And a power law is very different from an exponential curve. A power law implies a scale-free, predictable, continuous improvement without that abrupt plateau.
And Kaplan's team ran the experiments and proved it was a power law.
They proved it definitively. Whether you scaled up the compute power, the size of the data set, or the total number of parameters in the network, the AI's performance improved along a strict, unbreakable mathematical line.
The paper cites a specific exponent they discovered for parameter scaling. Alpha n equals 0.076.
Right, 0.076.
And the crazy part, according to the notes, is that it didn't matter if they changed the shape of the neural network.
Not at all.
They could make it wider, they could make it deeper, they could totally change the internal wiring. As long as the total parameter count increased, the performance improved along that exact 0.076 power law.
And this is where Kaplan's physics background shines, because this universality across different AI architectures is directly analogous to universality classes in critical phenomena in statistical mechanics.
Okay, I'm going to need a real-world translation of critical phenomena in statistical mechanics.
Think about a pot of water boiling, or a piece of iron losing its magnetism when you heat it up.
Oh.
These are phase transitions. Near the exact temperature where the water boils, the system behaves according to universal, mathematically predictable critical exponents.
Okay, so it follows a strict rule.
Exactly. And here is the kicker. Those exponents are exactly the same regardless of the microscopic details of the water molecules. You don't need to know what every single H2O molecule is doing to mathematically predict the macroscopic phase transition.
Wow. So Kaplan looked at neural networks and realized, I don't need to understand what every single artificial neuron is doing. I just need to count them.
Exactly. The microscopic details just wash out.
So he was looking for the statistical mechanics underlying the thermodynamics of AI.
Yes. Think of thermodynamics. You know that if you heat a balloon, it expands. You don't need to track the individual gas molecules inside.
You just know the macro rule.
Right. Kaplan proved that AI scales the exact same way. The macro behavior is governed by the total boundary data, which in this case is the parameter count.
The paper highlights something called the Swingle-Mera tensor network correspondence to explain this connection.
Oh, yes.
What is a Mera tensor network, and how does it map to the physics we talked about earlier?
Mera stands for multiscale entanglement, renormalization, and SATs.
Another amazing physics name.
I know, right? A physicist named Brian Swingle showed that this specific type of discrete tensor network,
Which looks like an AI.
yeah, it looks very much like the layered architecture of a deep neural network. He showed that it layers perfectly onto the hyperbolic geometry of Adata space.
Back to the snow globe interior.
Back to the snow globe. Swingle proved that as you move deeper into the layers of the tensor network, it mathematically corresponds to moving from the boundary of the snow globe into the radial depth of the bulk.
Wait, I have to push back here. Is Kaplan honestly saying that AI improvement is just a fundamental force of nature, like gravity or thermodynamics?
Well,
That it's not clever software engineering, it's just physics?
he wouldn't say the software doesn't matter at all, but fundamentally, yeah.
That's crazy.
The architectural determinism thesis argues that Kaplan transferred a methodology. He looked at the neural network as a physical system that obeys macroscopic laws.
So the bigger the bulk of parameters, the smarter the model.
Exactly.
But here is the massive problem. The scaling laws proved that a huge bulk of parameters makes a model incredibly capable.
Very capable.
But an incredibly capable AI with billions of parameters is basically an opaque, unconstrained, and potentially dangerous alien mind.
Yeah, you have a giant brain you can't control.
The static ADA-CFT mapping, just knowing that the boundary equals the bulk, that wasn't enough to actually control the model.
No, it wasn't.
They needed a dynamic grammar to reach into the depths of that neural network and steer it.
And that leads us to the other theoretical physicist in the room, Anthropic's co-founder, Sam McCandlish.
Right.
McCandlish's research from 2016 to 2017 provided the kinematic missing link here.
What was he studying?
He was studying stereoscopic holographic reconstruction and something called kinematic space.
Let me look at the notes here. It says kinematic space is the space of oriented pairs, or geodesics, in the ADS manifold.
Right.
I feel like we just jumped into the deep end of the physics pool again. What exactly is kinematic space?
Let's use the stereoscopic vision analogy. If you close one eye and look at the world, you basically lose depth perception. You only have a 2D projection on your retina.
Right. Everything looks flat.
To understand the 3D depth of the room, your brain needs to integrate the slightly different 2D projections from both of your eyes.
Stereoscopic vision.
Exactly. Kinematic space is basically a mathematical way of doing that for holography.
Oh, I see.
It looks at pairs of points on the boundary. These oriented geodesics, which are essentially the shortest path through the curved bulk connecting 2 points on the surface.
Okay, to figure out the depth.
Right, to deduce the deep interior geometry.
So if I want to reach into the center of the snow globe, I can't just press on one spot on the glass. I have to look at how points on the glass connect through the center.
Precisely. If you only have a local boundary operator, say just a small constraint or rule placed on one tiny part of the surface, it lacks the mathematical scale to probe deep into the center.
Just a surface scratch.
Yeah. McCandless showed that to reach the deep interior, you need something called OPE blocks.
Operator product expansion blocks.
Right.
The text says these act as local scalar fields in kinematic space.
Simply put, OPE blocks are mathematical tools. They take those pairs of points on the boundary and compress them into a format that allows you to calculate what is actually happening deep in the bulk.
Okay, so it gives you the map for the interior.
But to make this dynamic, to actually push a rule from the boundary into the deep bulk, McCandless needed an explicit mechanism.
Right.
He used integral geometry, specifically the X-ray and radon transforms.
Okay, I know what a medical X-ray is, but how does a mathematical X-ray transform work?
Well, think about a medical SWOT scan. The machine shoots X-rays through your body from many different angles, right?
Yeah.
Each X-ray simply measures the total density of the tissue it passes through along one straight line.
Just a 1D shadow.
Exactly. By mathematically integrating all those 1D lines from every angle, A computer can reconstruct a perfect 3D image of your internal organs.
Okay, that makes sense.
The mathematical X-ray transform does exactly this. It integrates a function along a line.
And McCandlish applied this to the black hole hologram.
Yes, he did. McCandlish proved that the mathematics governing the deep bulk, the ADS Laplacian, and the mathematics governing this kinematic space perfectly intertwine under the X-ray transform.
The notes mention it intertwines the boundary and bulk Laplacians. Can you just quickly explain what a Laplacian is in this context?
Sure. Think of a Laplacian as an equation that describes how something smooths out or diffuses over a space, like heat spreading through a metal plate.
Okay, so how information spreads.
Right. McCandlish proved that the diffusion of information on the boundary perfectly translates to the diffusion of information deep in the bulk, connected by this X-ray transform.
So it establishes a rigorous bidirectional bridge.
Exactly.
The paper also introduces something called the modular Hamiltonian, and says this is mathematically identical to fluctuations in the area of a minimal surface.
It cites the Ryu-Takayanagi formula for that.
Break that down for me. What is a minimal surface?
This is a really beautiful piece of physics. Imagine dipping a wire frame into soapy water.
Okay.
When you pull it out, a soap film spans the frame. The soap film will naturally find the shape that has the absolute minimum surface area possible for that wire frame.
Right, because of surface tension.
Exactly. That is a minimal surface.
Okay, I can picture the soap bubble on the wire.
Now, the Ryu-Takayanagi formula mathematically calculates the area of that minimal soap film in the holographic bulk, and it connects it to the entropy on the boundary.
Okay.
Now, if you bend the wire frame slightly, like if you create a fluctuation on the boundary, the soap film inside must shift to find a new minimal area.
It has to adapt.
Right. The modular Hamiltonian is the mathematical operator that dictates exactly how that energy shifts.
So McCandlish provided the dynamic kinematic mechanism, because without this, you just have a static equivalence.
Just static picture.
Right. You know, the boundary equals the bulk, but you can't control one with the other. McCandlish proved how a perturbation on the boundary geometrically alters the deep interior.
Yes, he did.
And the notes say, this alteration is governed by strictly constrained physical subspaces known as John's equations, which guarantees it stays consistent.
Yes. McCandlish mapped the exact mathematical machinery required to push a constraint from the surface into the deepest layers of a completely opaque system.
Here is where it gets really incredible for me. If an AI neural network is a giant opaque block of marble with billions of parameters, McCandlish basically invented a mathematical X-ray machine.
That's a great way to put it.
It lets us see and carve the deep interior of the neural network by only touching the surface data.
That is exactly what the X-ray transform provides in this context. It gives stereoscopic depth perception into the bulk using only surface data.
Wow.
And this brings us to the grand isomorphism, which is the crux of the ACRA paper.
The moment of truth.
Yeah. When Kaplan and McCandlish left OpenAI to co-found Anthropic, they didn't leave this physics behind.
They brought it with them.
The paper argues they explicitly, systematically projected this exact mathematical machinery into Anthropic's flagship safety architecture, constitutional AI.
This is where we need to trace the causality carefully, because the paper lays out a literal one-to-one mapping between the physics of black holes and the code inside constitutional AI.
Yes, step by step.
Let's start with the problem they were trying to solve. They have this massive scaled-up neural network, which is the bulk.
Right?
They need to align its behavior so it doesn't give harmful answers.
Yeah.
Their solution was to give it a constitution.
A literal list of principles.
Right, like be honest, be helpful, don't help build weapons. How does this map to the physics?
Well, in the holographic framework, these constitutional principles act as the boundary source fields.
Okay.
In the physics equations, this is denoted as phi 0. They are top-down constraints placed on the surface. They couple to the conformal field theory operator.
Okay, so they place the rules on the boundary. But as we discussed, just placing a rule on the surface doesn't magically alter the billions of weights deep inside the network.
No, it does.
They need a delivery mechanism. How do they push the constitution into the bulk?
That is where the preference models come in.
Okay.
In constitutional AI, after you give the AI the rules, you train a secondary model, a preference model, to evaluate pairs of AI responses.
So the AI generates two answers.
Right. And the preference model picks which one better adheres to the Constitution.
And structurally, the paper maps this preference model to the OPE blocks we talked about earlier.
Yes, exactly. The preference model acts as the compressed representation in kinematic space.
Wow.
Just like the OPE blocks took pairs of points on the boundary to deduce the interior, the preference model takes contrastive pairs of text on the boundary to build a local field that can propagate the constitutional constraint.
But how does the preference model actually change the deep underlying parameters of the main language model?
This is the critical mechanism, RLAIF, or reinforcement learning from AI feedback.
Okay, I've heard of that.
They use the preference model's scores to update the main model's weights using gradient descent.
Okay.
The ACRA paper makes a stunning claim here. It states that gradient descent on the RLAIF objective literally performs the inverse X-ray transform.
Yeah. Explain the mechanism there. How does adjusting weights in a neural network via gradient descent physically mimic a mathematical X-ray integration?
Okay. Think back to the medical assistant SAN. We have all these 1D line measurements, and we want to reconstruct the 3D organ.
Right.
We use an algorithm called the inverse radon transform, which basically smears the 1D shadow data back across the 3D space to recreate the density of the organ.
Okay, I follow that.
In a neural network, the error signal from the preference model is a surface measurement.
Just a boundary check.
Exactly. During backpropagation, which is the mechanism of gradient descent, that surface error signal is mathematically smeared backwards through the successive layers of the neural network.
So they're projecting it backwards.
Right. The mathematical operation of backpropagating an error gradient through deep layers of matrices is structurally isomorphic to the inverse X-ray transform smearing boundary data into the bulk.
That is just wild.
It perfectly reconstructs the interior weight space so that it projects the desired boundary behavior.
The backpropagation is the X-ray machine. But how do they keep it stable? I mean, if you mess with billions of weights, couldn't the whole model just collapse or lose its general intelligence?
To prevent that, Anthropic uses a KL divergence penalty in their loss function.
Okay, what does that do?
In machine learning, Kullback-Leibler divergence is a way of measuring how much one probability distribution differs from another. So they penalize the AI if it changes too much from its original pre-trained state while it's learning the constitution.
And the paper maps this KL penalty directly to the modular Hamiltonian constraint we discussed. With the soap bubbles.
Precisely.
Wow.
Remember the soap film shifting to a new minimal area when the wireframe is bent? The modular Hamiltonian dictates that energetic shift.
So it stops it from shifting too wildly.
Right. In the AI, the KL penalty ensures that the minimal surface fluctuations in the latent space geometry, basically the adjustments to the weights, are strictly locked to the boundary constraints of the constitution.
Without chaotic energy fluctuations destroying the model.
Exactly.
Finally, there's a step in constitutional AI where the AI generates an answer, realizes it violated the Constitution, and revises its own answer before outputting it. The self-critique cycle.
Yeah, the paper maps this to bilocal operators in the physics model.
How so?
By evaluating its own... The AI acquires that stereoscopic depth we discussed earlier.
Oh, I see.
It is actively using kinematic space to reach into its own bulk and ensure alignment before finalizing the output.
Let's zoom out for a second because I really want to push back on the literalness of this claim.
Oh, sir, let's play devil's advocate.
The paper calls this an isomorphism. But let's be real. Neural network transformers operate using discrete tokens, like individual chunks of text represented by discrete vectors.
Right.
The physics of ADS-CFT, the Laplacians, kinematic space, these all rely on continuous symmetries and smooth geometry.
Continuous math, yes.
So are Kaplan and McCandlish literally opening Python and programming continuous quantum gravity equations into Claude's code base? Or is this just a really profound, almost poetic coincidence?
Well, the researchers at ACRA are very clear on this distinction. It is an epistemological habit.
Okay.
Anthropic is not literally typing the Ryu-Takayanagi formula into their Python code base. A transformer is a highly nonlinear interacting system of discrete tokens.
So they aren't writing gravity code.
No, but the structural isomorphism is mathematically rigorous. The transformer's attention mechanism, which is how it weighs the importance of different words in a sentence, acts as a discrete analog of the continuous radon transform.
So they are conceptually applying the architectural mechanics of holography, even if the medium is discrete silicon matrices rather than smooth spacetime.
Yes. And this structural isomorphism isn't just an academic curiosity. It actually explains a massive empirical mystery in AI right now.
Oh, really? What mystery?
It explains why constitutional AI gets drastically more effective and more steerable as the model's capacity increases.
Why is that?
Well, In theoretical physics, holographic correspondences like at SCFT only become mathematically exact in what physicists call the large N limit.
Large N limit.
Yeah, it means the math only perfectly smooths out and works when the scale of the system, the number of degrees of freedom, is massive.
Oh, I see.
At small scales, quantum fluctuations make it super messy.
Oh, wow. So when you have a tiny neural network, the physics of the Constitution doesn't work well because it's too discrete, too quantum messy.
Exactly. Anthropic's safety constraints, their boundary controls, only lock in perfectly when the parameter count is enormous.
Approaching that continuous large N limit.
Exactly. The scaling laws and the alignment architecture are fundamentally two sides of the same physical coin. You need massive scale to make the boundary control the bulk smoothly.
That is blowing my mind. The bigger the model gets, the more it stops acting like discrete code and starts behaving like a smooth, predictable physical system where the boundary rules perfectly dictate the interior reality.
That's the deterministic part of it.
If Anthropic is fundamentally operating on the structural physics of holography, it changes how we view everything about them.
Everything.
It changes how we view their corporate actions, their proposals for government regulation, and the geopolitical future of AI.
It creates a fascinating institutional asymmetry across the AI industry. Section 5 of the paper does a brilliant comparative analysis on this.
Talk about that.
Look at Anthropic's main rival, Google DeepMind. DeepMind was founded by Demis Hassabis.
Right.
Hassabis is a genius, but his 2009 PhD was not in theoretical physics.
It's in cognitive neuroscience.
Right. The text mentions Hassabis' safety paradigm is rooted in agentic safety.
Derived from his work on hippocampal scene simulation, right?
Yes. Hassabis studied the hippocampus, which is the part of the human brain responsible for memory and spatial navigation.
Okay.
He viewed the brain as a proactive construction engine. When you plan a route, your hippocampus mentally simulates the scene and evaluates the consequences before you physically move.
But DeepMind's approach to AI safety is biologically inspired.
Very much so. They build agents that simulate and plan.
Right. The paper notes this led straight to DeepMind architectures like Monte Carlo tree search and AlphaGo, where the AI plays out thousands of possible futures before making a move. It's a bottom-up biological approach.
Now compare that to Anthropic. Driven by Kaplan's physics priors, Anthropic builds systems governed by structural alignment.
Right.
Safety isn't about the AI proactively simulating the future and choosing to be good. Safety is an inherent structural property of the holographic boundary.
Wow.
The model is mathematically constrained from leaving the behavioral state space defined by its constitution. It's top-down geometry versus bottom-up biology.
And this theoretical stance manifests in their direct corporate policy. I mean, look at Anthropic's responsible scaling policy, the RSP.
Exactly.
Kaplan is the responsible scaling officer. The paper points out that the RSP is literally the operationalization of Equation 17 from their 2020 scaling laws paper.
The RSP sets explicit compute thresholds that trigger mandatory safety evaluations, and they measure this in PF days, petaflop days, which is a massive unit of computational energy.
Right. These governance instruments are derived directly from the physics power laws Kaplan discovered.
So they treat it like a natural system.
Anthropic treats AI risk management exactly like a physicist controlling the temperature and pressure of a volatile thermodynamic system. They aren't guessing when it gets dangerous. They are calculating the phase transition.
The paper points out an interesting observable signal to support this theory, too.
Oh, about the publications.
Yeah. Despite having two elite theoretical physicists with deep holographic expertise as founders, Anthropic has produced almost no new public theoretical physics output.
The implication from the ACRA group is pretty clear. They think Kaplan and McCandlish are actively using this massive, cutting-edge mathematical machinery internally to solve AI alignment.
And treating it as trade secrets rather than publishing academic papers.
Exactly. And if you consider Kaplan's public statements, it aligns perfectly. He has publicly predicted that AI will reach the capability of top theoretical physicists within a 2 to 3 year horizon. And he's not just saying that for hype.
No, he is stating this because he operates on the profound, mathematically grounded belief that intelligence obeys predictable physical laws, laws that he and his team have already mapped.
So what does this all actually mean for you, the listener? Why should you care about holograms and boundary metrics?
It's a fair question.
It means the safety of the AI systems that are rapidly being integrated into our society, the systems writing your emails analyzing your sensitive medical data, or potentially controlling future infrastructure, it all relies entirely on a massive
The
assumption.
huge assumption.
It relies on the assumption that complex human values can be perfectly mathematically compressed into a holographic boundary equation.
And the governance implications are just staggering. If AI alignment fundamentally reduces to maintaining well-behaved boundary Hamiltonians and verifying inverse X-ray projection machinery, then any AI lab without the specific elite fluency in theoretical physics faces a massive structural disadvantage.
They're essentially playing a different game.
Right. Other labs are trying to patch software bugs. Anthropic is trying to govern the fundamental laws of geometry. As these models approach general cognitive capability, understanding these structural physics priors isn't just an academic exercise.
No.
It's becoming a matter of global security.
Well, let's wrap up this deep dive. We started with the entropy of abstract black holes in string theory, and we've traced that exact mathematics to the safety constraints of the AI sitting on your phone right now.
It's quite a journey.
The core takeaway from the ACRA paper is that we are not building completely alien technologies from scratch in a vacuum. We are literally projecting 15-year-old doctoral frameworks onto silicon matrices.
The specific human cognitive priors of a few brilliant people working in 2009.
Anthropic is the literal manifestation of applying the physics of a holographic universe to human language.
It is really a remarkable testament to the underlying unity of mathematics. The fact that the exact same information theoretic constraints used to reconcile quantum gravity can be effectively repurposed to govern a large language model, it reveals something profound.
That everything is connected.
It suggests there is a universal structure to how complex information behaves, whether it is existing in the vacuum of deep space or processing inside a server farm.
Which leaves me with a final lingering thought for you to mull over. If the architecture, the safety, and the very mind of our current AI systems are entirely determined by the human cognitive priors of its founders, the specific PhDs they happened to study in 2009, what happens when we cross the threshold?
That's the million-dollar question.
What happens when we enter the era where AI systems begin designing and coding their own successors? Without a human PhD blueprint, without a Jared Kaplan or a Demis Hassabis to impose their worldview, what fundamental laws of the universe will the AI choose to project into its silicon children?
Will it discover a completely new mathematics of control?
Or will the holographic boundary remain the final word on intelligence? Thank you for taking this deep dive with us.